Today we want to talk about vectors and vector operations, the point of doing these things, and then how we're going to operate with them. That's an important thing that we always do in math class. Like, here's a thing, and here's our operations that we do with that thing, and then here's what that thing means. And then sometimes even, here's why we care. That's always a dangerous thing to say, is like, well, here's why we care about this thing, and then give an example, because students will always be like, well, I don't personally care about that, right? But anyway, vectors. A vector is a quantity with magnitude and direction. A vector is a quantity with magnitude and direction. As opposed to most of the stuff, the numbers that we've worked with so far, which are scalars. Now that I've brought up vectors for quantities, I need to bring up scalars, which are just magnitude. So a vector is a quantity with magnitude and direction versus scalars, which are just magnitude. We usually represent the direction with an arrow, and we represent the magnitude with length. So direction, we represent with an arrow. Spelled W wrong. There are no R's in W. It's spelled with two V's. We represent direction with an arrow and magnitude with the length of the arrow. There's a vector V. Then we can have some other vector, let's say W. In this case, we can see that V and W have different directions, and it looks like they have different magnitudes. Our notation for vectors, we'll put a little arrow above the letter, the name of the arrow, the vector. So we're going to use lowercase letters as names for vectors, and we'll indicate that they're vectors and not scalars by putting an arrow over them. If we're typing, we might use bold. But since we're writing, we don't have bold, we'll just put an arrow on top. when we're typing, we usually use bold because it's, well, historically, it's difficult to make a letter with an arrow on top of it. So back in the day when typesetting was actually setting the type into a machine to print things, we're like, the printer was like, dude, I don't have a V with an arrow on the top of it. I'm just going to use a bold V. Like Newton's original notation for derivatives, which he didn't call derivatives, I think he called them like fluxions, was like the name of the function f, but with a dot directly over the top of it. And they were like, oh, dude, we don't have an f with a dot over the top of it, and we're not going to make one for your stupid book. So then there was like, oh, we'll just put an apostrophe afterwards. So that might be not a true story, but it sounds so reasonable. Which is like the worst argument for anything ever. It's like, oh, that sounds reasonable. I mean, that's just like, that's a shit argument, but that's what we got. And you've heard it from me now, and so now it's true, which is kind of hilarious. Never believe history. Just kidding. Never believe unverified history, because I just gave you a bunch of unverified history. No, that's like the story that I've been told, but I've got no way of verifying it. So, or I've got not enough energy to verify it. I'm like, all right. It's like the Pythagoreans drowning a guy. I mean, that's the story, and you can kind of believe that it's true. But, I mean, have you heard the story of the Pythagoreans? So the Pythagoreans, like the ancient Greek people, like Pythagoras, he was, they used to believe that all numbers were rational. We just didn't know the ratio yet. They just used all numbers are rational. And then they're like, oh, what about the length of the diagonal of a square? And like, oh, we just don't know what the ratio is yet. What about pi? We just don't know the ratio of just don't know the ratio yet. What about the base of the natural logarithm? It's like, oh, we don't even have that yet. Go away, right? So they're like, oh, no, all numbers are rational. We just don't know what the ratio is. Then someone comes along and says, guys, check it out. I can prove that the square root of 2, the length of the diagonal of a square, is irrational. And they're like, oh, close the door. He's like, oh, okay, what do you got? And then he goes through and he proves that the square root of 2 is most definitely an irrational number. It cannot be expressed as the ratio of two integers. I'm like, oh, very interesting. You do realize that all numbers are rational is kind of one of our foundational beliefs. It's like, oh, yeah, this kind of really throws a wrench in that, doesn't it? It's like, well, yeah. Hey, let's go fishing. Yeah. And so the story is they gave him the old Fredo treatment. Yeah. So they're like, oh, well, we can't have this person coming along with actual proof, verifiable, unquestionable proof that the square root of 2 is irrational. It attacked their beliefs so hard that rather than just like pivot and say, oh, well, look at this new cool thing and be happy about it, they murdered the dude. Yeah. And anybody that came along, it's like, oh, hey, this guy showed me this square root of 2. Have you seen him? I wanted to talk to him about it. And like, oh, really? I think he went fishing. Let's go. Oh, I'll take you out there to see him. Hey, where'd that guy go? Don't tell me. It's the square root of 2 thing. He's like, well, yeah, I was going to ask him about it. It's like, oh, come fishing. All right, anybody else need to find the guy that went fishing with the square root of 2 thing? And then they're like, oh, yeah, totally. It's like, oh, all right. We're going to need a bigger boat. So, and they start, and then eventually the word just gets out. I mean, you just can't keep a lid on that kind of stuff. You know what I mean? Don't know. So the question is, why was it so important for Pythagoreans to believe that all numbers were rational? I don't know. It was just one of their foundational beliefs that they decided on, and they decided it was really important. And the fact that they couldn't prove it one way or the other probably made it harder for them to get rid of. They just started believing it harder, and that's really where the problem came in. Do you know what I mean? One of the most important things, one of the things that you're doing here at school is making your life way more difficult. I'm not just talking about now. I'm talking about your life from here on out. The more you know, the harder your life is going to become if you do education correctly. The whole point of this exercise is to make you miserable, not just like here and now. I'm really good at making you miserable here and now. That's easy. I can easily make you miserable for an hour every morning. That's no trouble. I'm here trying to make you miserable for the rest of your life. Because they say, as they say, ignorance is bliss. And so what does that mean on the other side? Knowing stuff, it takes effort. Look how easy it would just be. Look how easy it would just be as an individual, on an individual basis, to believe something super hard and never question it. And then when the people come along that do question it, you just cut them out of your life. I mean, you can't go, you're not like a cult leader or anything like that, so you can't just like murder the people that question your beliefs, like Pythagoras. I don't know if Pythagoras personally did that, but I mean, yeah, he had like a fanatical following. Yeah, he was kind of like a cult leader at a certain point. I mean, you could tell he's a cult leader. I mean, who else would name a whole fucking theorem after themselves? I don't know if that's how it works, but the Pythagorean theorem, he didn't come up with that shit. That was known for possibly thousands of years before that. That's like an old ass result. You know what I mean? It's an old result. But the way I picture it is Pythagoras has his little cult following. And they're going, all right, the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. And all of his followers or students were like, oh, dude, shit, that's awesome. And I go, I know, right? And they're like, oh, did you come up with that? And he's like, in the moment, I just imagine the moment. He's like, oh, fuck yeah, I came up with that. That's the Pythagorean theorem, named for me, Joe Pythagoras. And it's like, oh, Pythagorean theorem. And then like other cultures showed up and like, oh, hey, what's up, Pythagoras? How's your class going? It's like, oh, great, I just taught him Pythagorean theorem. And they're like, oh, what the fuck is that? And I go, it's the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. So, well, we've known that for a long fucking time. It's like, oh, not anymore, you didn't. It's the Pythagorean theorem. And I go, what the fuck, man? You're setting us back. It's like, oh, because racism, dude. Fuck you. So I don't know. I think in my mind, that's how it went. Students were like, oh, wow, that's pretty cool. Did you come up with that? Yeah. That's all me. They didn't have the internet back then, so what are you going to do? Think about a song, right? Think about a song. It's like, oh, wow, that song is awesome. Without the internet, you could just be like, oh, yeah, that's my song. Yeah, it's Pascal's triangle. Name for Pascal is not a Pascal thing. Like most of the time when something is named for someone, unless it's like Cauchy, Euler, or Gauss, it's probably not that dude's thing. Yeah. Anyway, what are we talking about? Oh yeah, vectors. Sorry, I got distracted. Because I'm worried there are some teachers that would probably like murder people when they get disagreed with. I don't know. It seems a little strong arm to me. All right. So our notation for vectors is going to be a lowercase letter with an arrow over the top. The length will be, we'll just draw a longer one. And for, yeah, oh, I've said all those things. Now, we need to think about some of the operations that we're going to have on vectors. The first operation we need to learn when we're dealing with anything is the first operation, addition. Addition is always the first operation. Like all your algebra, that's just based on addition. It's like, well, how can we multiply? What do we do when we want to add things and they're all the same? It's like, well, that's what we got multiplication for. Then what if we want to multiply things and they're all the same? That's what exponents are for. They're your big three operations of arithmetic. So we need to do some operations. We need to learn the operations on vectors. Here are the operations that we're going to learn or be reminded of. I don't know your class background at this point, but there's vector addition. There's scalar multiplication. And there's two kinds of vector multiplication. What are the two kinds of vector multiplication? Because I know some of you know this already. Dot product. I heard you. I heard you. I will give you your moment. Dot product is also called the inner product or the scalar product. So other places you might hear dot product because that's the symbol that we're using to indicate that multiplication. We're just like putting a dot. So that's why we call it the dot product. It seems kind of it's kind of like on the nose, but seems a little simplistic. So I think that we probably came up later with inner product. Also called scalar product. But it falls in the category of a multiplication. We're not just calling it a multiplication. It acts like a multiplication does. I know that you all don't really haven't really been taught what it means to act like a multiplication, but I assure you, it does act like a multiplication. I know you all can multiply, but you don't get to learn about multiplication until like way later. It's weird. What's the other kind? Cross product. Dot product is the one with a cosine. Cross product is a vector product. So the dot product is a scalar product. We're going to multiply two vectors and come up with a scalar and then figure out what that means. The cross product is a vector product. We're going to multiply two vectors and come up with a vector, and then we'll talk about what that means and then why we care. And then you can explain to me why you don't care as an individual. That's fine. That's your problem. They both act like multiplication. So they're both a multiplication of vector multiplication. Multiplying vectors together. So we're going to have two kinds of vector multiplication. One of them will be V cross W, and the other one will be V dot W. And they mean different things, and they'll have different mechanics and different uses. Let's go ahead. The dot product is the one where it's the product of the magnitudes times the cosine of the angle between them. So that's the dot product, or it's the sum of the products of the corresponding components. That's the dot product. The second one is the cross product. That's where we take two vectors and we calculate a vector that's perpendicular to both vectors. That's why we care about the cross product. So one of these days, I'm going to be like demonstrating this, and it's like it's going to be misinterpreted as some kind of gang sign. It's like normal vector gang, and the normal vector gang is going to be like the antagonists of the tangent planes. So I'm like, oh, for the cross product, we like take two vectors, we multiply two vectors sitting in a plane, and we get a vector that's perpendicular to both. And then I'm like, oh, vector perpendicular to both. And then someone's like, oh, nah, son, tangent planes. And then I get shot. So I mean, that's in my mind, that's what happens. My mind wanders when I'm standing up here talking about math. I don't know if this is a more coffee problem or a less coffee problem, but I know what solution I'm going to apply. Let's talk about vector addition. Now, right now, our vectors are these two arrows, and you're all thinking, dude, just write the components. I'm like, oh, we'll get to that. Cool your jets. So we need to visualize a vector addition. To add vectors, we just tack the two vectors together, tack the end of one vector onto the front of the other vector. So with vector addition, if I draw the vector v, this is the same vector as my original vector up here, and I tack on the vector w, tack the vector w onto the end of it. Then I just go from the start of the whole process to the end. That's going to be the vector v plus w. Now, at this point, you're like, well, okay, this is a nice visual representation of vectors, but dude, you just called that addition, and addition needs to be commutative. Multiplication, not so much. Addition needs to be commutative. You're going to call something addition, a plus b has to equal b plus a. And if we add the vectors in the other order, if I draw first at the same starting point, the w vector, and after that, attach the v vector, notice I end up at the same place. Note that v plus w is equal to w plus v. Why did I color code it? So now I got to switch pen. If we're going to call something addition, it needs to be commutative. Questions? V plus w is equal to w plus v. How's everybody okay? I told you Calc 3 was the easy one. So scalar multiplication is where we scale up the vectors. That's why we call them scalars, because it makes them longer, it makes them shorter, changes their direction. So if I have the vector w, do I have room right here? No, right here. If I have the vector w, if I multiply this vector by a scalar, I just make it longer. So 2w will just be two of these. I take a w and then put another w on the end of it. And we literally draw two w's. Arrow still only goes over the w, the 2 is sitting outside of that. It's 2 times w. It's two w's. Also note that this means w plus w, which makes sense because w plus w should be 2w. That's how numbers work. So the vector addition and the scalar multiplication, they're definitely going to be going together. We can also multiply by negative scalars, and that would change the direction. This is exactly what we thought would happen. I don't have to explain this to you. This is if I just told you to guess. If I say, here's an arrow, represents a vector. What do you think I'm multiplying by 2 would do? This is what you would guess anyway. It's only because it's 8 o'clock or we started at 8 o'clock on a Monday that I'm like, let's just draw pictures. and talk over it. Partially because my style of running a class doesn't lend itself as well to discussions. So I could be like, oh, what is 2 plus 3? And then we could literally just wait for a whole hour before anybody says anything. Because then it would become a competition. No. I've already tested my theory out. It becomes what I call the waiting game. And you all know that I'm less patient than you. So if I'm like, oh, so what is 2 plus 3? And it's like, you'll wait. And then like in your minds, it's just that scene from Braveheart. Hold. He's getting more bored. He will break. And then eventually I go, okay, 2 plus 3 is 5. And then I'll move on. But that's dangerous because sometimes I'll be like, oh, 2 plus 3 is 6. And I can just continue to move on. And then you're like, oh, should I say something? And now the waiting game is working against you. Also, 0 is a scalar. If I multiply this by 0, I just get the point. But this is not just a 0, the scalar. This is 0, the vector. So we can have a 0 vector. That's what's going to happen if I multiply by the scalar 0. That's also what's going to happen if I take a w and add a negative w. It's like I'll walk over there, now walk back. Where are you? Where we started. Notice if I take w plus negative w, get 0, just like we would guess. How's everybody okay? Easy? Yes. That means I need to make it harder. Oh man, we should have said yes. That would just make it very harder. So I mean, there's no like difficulty setting. So let's throw in components. A lot of times we're going to describe vectors with components. We like to describe vectors with components. It's going to look like coordinates, but it's not going to be coordinates, except for those times where they represent coordinates. All right, but that's it. That's it. We can have position vectors where they kind of represent coordinates. So we like to describe vectors with components. So this vector up here, v, is 3, 3. B and W are sitting in R2. So I need 2 components. So we have different ways of listing these components depending on what we want to do at the time. Here's your Calc 3 style. Here's your linear algebra style. Here's your physics style. I mean, that's 3 plus 3. See, I wrote 3. Oh, look, an eagle. I actually could have led with this, but I like to draw little arrows. The vectors I hat and j hat are unit vectors. So in this last one, I hat, I was taught to read the I, instead of putting an arrow over the top, I put a little caret over the top. I don't know if this is still done. And this was read to me as I hat, and I can't get rid of it because it's I with a little hat on it. I'm like, oh my God, that's so fucking cute. I'm never getting rid of this notation. It's also perfectly acceptable just be like, oh, it's just a I, but a vector. So calm down, dude. And this is specifically the vector 1, 0. or 1, 0. I hat. Are they older than me or younger than me? So he's way younger than me. So it might still be going on. I am trying to get Ever to be like all I hats. And then like you go to an international conference where everybody's supposed to be like mature. And you're gonna be like, oh yes, we'll take I hat. And you're like, oh, excuse me, what did you say? I hat, because it's an I with a little hat on it. And then they'll be like, oh, Americans are so fucking stupid. And it'll be awesome. It'll be awesome. Trust me. This is why I don't go to international conferences. Also, I don't like planes. What's that? Oh, so in linear algebra, we describe vectors as like n by one, like one column matrix. So it's another way to interpret vectors. And it's consistent. Interpreting a vector as a column, just a one column matrix, the math and the operations work out, and the interpretations still work out as far as matrix times a vector. Same thing as a matrix times another matrix. So we can use pointy brackets. We can write them as vertical single column matrices, or we can use them with our standard basis vectors I, J. So the vector W, it looks like we go 2 in the x direction and -1 in the y direction. So up there, the vector W's components would be 2 in the x horizontal and down 1 in the vertical, or 2, -1, or 2i minus j. Now, I know for some of you, this may be your first introduction to operations on vectors. So doing the vector addition and our scalar multiplication with the vectors as components, if I just do that right now, vectors will make complete sense. It's like magic. All of a sudden, you'll even understand dot product and cross product. But I have to do these operations right now. If I do these operations like right now in the next 2 minutes, then no problem. Everybody will completely understand vectors from here on out. You won't even have to do any work. It even makes vector calculus easier. I don't know what the magic is, but it's some magic. If you do introduce this and on the same day introduce how it works with components, everybody just understands you. So let me write down what the sum of these is. Do these operations up here with the components so that everybody can instantly understand. Because if we don't do it right now, we're going to have to work through this class at the normal rate. You're just not going to understand shit. And you're going to have to do work and homework and all that other stuff. And I can't just cancel the rest of the class because everybody instantly understands things like magic. So let me do these right now so we don't have to work for the rest of the semester. Oh, look at the time. That's it for today. I will see you all on tomorrow. Everybody have a good day. Thanks for playing.